All right, so as we're switching here, I'll do a quick intro with Mark Malik. He's our Senior Field Application Engineer, and he will be presenting on No Compromise Needed, reintroducing the two-layer PCBs.
Excellent. Welcome everyone to this session. We're going to be talking about two-layer PCB designs for a particular buck converter and kind of the importance of two-layer versus four-layer and the trade-offs here we have listed, EMI in terms of thermal performance. So I'm Mark Malik. I'm a senior FAE with MPS, supporting OEM and Tier 1 customers in the Midwest region. I have about 20 years of experience in various aspects of automotive design for the most part at the OEM level, doing system level design as well as hardware for automotive and military, and most recently been doing field application support for various applications, power supplies, SerDes, motor control, LED control as well. So here's a quick view of the agenda. There's a lot of points here, but we'll get through this fairly quickly. We're going to go through our motivation on why we did this, taking a look at what the differences are, four-layer versus two-layer in terms of the trade-offs that we noted. We'll take a quick look at the MPQ 4323 and its features and kind of why we're targeting this device. We'll take a look at the schematic, the floor plan or component placement layout, the recommendation, and we'll spend a lot of time focusing on our recommended one, and I'll show you what that what the goal was there for this particular exercise. We'll look at the different layers of the boards, filter layout as well, and then we'll take a look at the results, the thermal effects, and the EMC results as well, and some comparison versus competitors as well. So our motivation for doing this, basically two-layer versus four-layer, there's a cost difference. If the application doesn't require it, can we get away with a two-layer design versus a four-layer design and save ourselves some costs? On the trade-off side of things, we do have to meet our EMC limits, whatever we're given, and we'll take a look at that again, some CISPR test limits in this particular case. But in general, it's going to be a little bit tougher to meet EMC in two-layer design versus four-layer design, and we'll take a look at why that is the case. Ambient temperatures for different applications are going up, and this may not be necessarily in cabin versus under hood. This could be as simple as there are certain applications where you're in cabin, you might have a plus 85 degrees C operating ambient, but for various reasons, your operating temperature could be higher. For example, you could be near the windshield and in the sun in different locations where the ambient temperature could be higher for your application. So we did an experiment, and we're showing the panel on the right-hand side here. And I'm not going to go into detail on each of these designs, what their shortcomings were. We're mostly going to focus on kind of the good one as we deem it. But you can kind of see in the different layouts that we have here, we did different separations on ground, and we had some presentations on that yesterday. We took a look at isolating the filter input, isolating ground around the power supply, and different routing techniques for VIN as well. And you kind of see some of the differences here, but mostly I'm going to focus on our I'll say best of the best design. So a four-layer versus two-layer, obviously this is not representative, but it is to scale in terms of a standard FR4 PCB thickness, right? So we're looking at a 1.6 millimeter thick board in the four-layer versus the two-layer. And you can see in terms of EMI, the loop that we're going to have from power or any signals on the top layer to the return on the ground is significantly different, right? We're looking at something that is 8 times longer in terms of our loop. So we should expect to see some potential trouble there in our EMI performance. The other thing is from a thermal resistance standpoint, we are going to see a corresponding increase in thermal impedance to the bottom layer. Now, there are different aspects of this, and a thermal design could be a whole nother session on its own, but when we are able to use that internal ground plane, we are able to spread the heat more, even though we don't have the external convection available. In most of these applications, we're in a box anyways. Convection may be a luxury that we don't have for these applications, but that's something that at least that additional ground layer gives us better thermal performance. And we can kind of see that here in these pictures as well. So we have a difference, and on the left is all 4-layer. So we have the 4-layer picture, the thermal picture here on the left, and the 2-layer thermal picture on the right. And you can see we have roughly 12.2 degrees C difference in terms of a similar layout. So this is running for 2 hours. So we've reached steady state, 430 kilohertz at 3 amps load. So there is definitely benefit for a 4-layer in certain applications, so that may become a necessity. Taking a quick look at the 4323. So one of the reasons we have selected this particular device is for cost sensitive applications, generally smaller 3 amp current may not, it certainly may not be targeted towards a big application. And this device is an 2 by 3 millimeter package. So this is a very small device, good power density. There are a number of devices with different current load, or the current levels on the output, so we can scale the inductor accordingly and maybe help ourselves EMI wise. Up to 96% efficiency, so this device will help us get maximum power out for these different applications, even in the high ambient operating temperatures. It does have an adjustable frequency. We do have adjustable outputs and fixed outputs as well, and we also have spread spectrum available on this device to help with EMI, as Christian talked about earlier. This device does have the symmetric VN, so that'll help us there as well. And it does have a low dropout. So if we're providing bias for LED applications or things like this, and we have to have 5 volts, when we get into a cold crank situation, we have pretty good dropout performance on this device as well. Here's a quick look at the schematic for the EVB, and I'll quickly touch on some points here. One thing to note, depending on the OEM requirements, we may need to pay special attention to the input capacitors, right? We may need flexi-term caps on C2 and C3, or there may be requirements for having these 90-degree mounted capacitors. The reason is with the board flexing and vibration, there is a possibility of the capacitors becoming cracked and shorting out, and that would be a short from battery to ground, not necessarily a lower voltage. And so that can produce undesirable results. So there may be that requirement for these 90-degree mounting on the input line, and we show that on this particular EVB. We do have a spot for a ferrite bead for higher frequency filtering, but in this particular case, and you'll see it in the layout, that's actually shorted out by copper in the PCB layout. So we only have this 2.2 microhenry inductor. We have the 47 microfarad aluminum electrolytic providing some dampening. Given that this might be a small application, you know, a question that we do get sometimes is, can we eliminate this aluminum electrolytic because it can be tall? The answer is yes, we can, but we need to be careful about adding some ESR that this aluminum electrolytic would be providing normally. And the reason is the frequency response of this system on the input can have a pretty high Q at some resonance point, and we need some resistance here to help dampen that. I'm not going to cover that in detail, but just know that that is a possibility to get rid of the aluminum electrolytic, but we need to simulate it somehow with some series resistance there. We have our input caps that'll be directly next to the IC, and we'll take a look at placement and layout in later slides. We do have resistor here to set the frequency. Because we're trying to maximize the power out for this particular exercise, we are switching below the AM band so we can have a higher efficiency and get the maximum power out of this device in this particular exercise. So correspondingly, you can see a higher inductance value for the lower switching frequency. We do have a boot resistor here populated to help slow down edges if we need it when EMI, but we'll take a look at that later on. And then we also have our output capacitors in the schematic here and the feedback network as well. Taking a look at the layout, this is the actual board. We do have the input filter side here with the ceramic caps in our T configuration that we talked about previously. The inductor filter and the aluminum electrolytic. What we did was, because we wanted to try and keep everything on the 2 layers for this exercise, we split the input to either side to have our symmetrical current flow as much as possible. Current balancing is not going to be perfect, but we do want to try and keep these elements in parallel so we have our somewhat equal and opposite currents, as well as try and maintain parallel parasitics to reduce that effect as well and maximize the performance of these high frequency components near the buck converter. One thing I'll note is we do, and we'll take a look at that later, we are mounting everything on one side, which also can be a cost benefit. We're only mounting components on one side versus 2. And we also are including test points in this design so that we're also trying to make sure that we can pass with a manufacturable type setup that customers would typically do. So even on the switch node, which gets kind of tricky trying to minimize copper, we do have test points there. You'll notice that on all the nets as well. On the left, we have the top side layout. On the right, we have the bottom, and the bottom is mirrored, so it's sitting right over the top. It's not opposite in this particular case. I've tried to color code the nets, just how they are in series. So you can see power supply battery connection here through our reverse blocking diode into our filter section, and then this is the VN split. This pinkish magenta color is our switch node, and you can see the bootstrap here as well. And we'll talk a little bit about that more coming up, but you can also see that circuit also passes on the bottom layer. This is a circuit that we need to be concerned with a little bit because this is a switching current node for the high side MOSFET control. We need a voltage higher than the input to control that MOSFET fully. So that's the reason for this circuit over here, and that's pretty standard on off battery buck converters. On the bottom, we have V out trace. So this is going back to our feedback network. So you can kind of see from this blue color on the top side over to these components. This is the feedback network with the resistor divider, as well as we have a optional placement for our feed forward capacitor. This blue trace here is just the power good. This is a digital signal with no frequency content. It's either on or off based on the status of the part. So we really don't have to be too concerned with that guy. But then we have the bootstrap power supply coming over to the device. So that's this viet here coming over here. A little bit of a necessity because we don't want to break the VN path into the device. So that was a conscious decision to put that bootstrap power supply on the bottom. We'll see later on, it doesn't have a significant effect on the EMI results, but from a layout perspective, we want to keep the VN of the buck a little bit cleaner and neater than the bootstrap. There's less energy and not as big of a concern on the DIDT for the bootstrap. So here's a more detailed view of this and going through the different aspects that are key both for a thermal and EMI perspective. So we have this very large pore for the VN. Maybe not always practical depending on the application, but this is kind of how we can get the best thermal performance, allowing the heat to radiate out from the device, as well as these symmetric VN paths for the input current. We're trying to keep the switch node small. Obviously, we do have that test point that we included in there for the manufacturing test, but overall, the copper is pretty small. I'll show later on the, actually, I will go back real quick just to point this out, because I think it's better in this picture. Actually, it might be tough to see, but for this particular inductor, because we're going with one side component mounting and a 2-layer board, what we decided to do was test this with an inductor that only has a connection on the bottom side. So referencing some of the material from yesterday, the inductors that have the contacts up the side that would allow for optical inspection, so that's a bit of a trade-off there. But that metal contact will also act as an antenna and does have the ability to potentially radiate energy up to and past the input filter. If we get that kind of coupling in our system, we're more than likely going to have trouble with EMI. So one of the decisions we decided that we made was to use this type of inductor where we don't have that type of antenna on the inductor itself. So we've got a small switch node. We've also got bottom only mount on the inductor, so we don't have that antenna there. P ground is a large plane, and it's all of the screen, and we have lots and lots of stitching. I would say that this is a bit probably overkill, but having quite a bit of ground stitching is necessary, both from a thermal perspective as well as EMI, especially around the switch node and the input caps, so that we have small current paths for the return current. The signal pins, you'll notice in general, you probably wouldn't need such large traces, but what we're doing is we're intentionally making these traces large to just maximize the amount of copper we have, just so we can get the heat spread away from the device. It wants to spread radially away from the device. So breaking up the copper does not help. As much as possible, we want to keep this solid copper around the device. Obviously, there are going to be breaks. That's just the way it's going to be in terms of how we actually have to lay out and route the device. But the important takeaway is, however much copper we can add to help cool off the device, we really need to do that. So we try to avoid routing traces on the bottom layer, but what you'll notice here is that we have a few signals on here. So we put the feedback on the bottom, and that is in part to keep it separated from any noisy signals that we might have. If we go back and look at the top, so this is the V out, which should be fairly quiet, but we have the switch node over here. We don't want to bring that trace near that switch node to possibly pick up additional noise. So we have this via over here, which is here on the output caps, to bring that back on the bottom layer. And we're keeping that away from those noisy DVDT and DIDT nodes. The PG, again, it's not so critical. But then we have the boot trace, which is critical, but we have quite a bit of ground around this, isolating it from PG and certainly from feedback, because we certainly don't want any potential coupling. We want distance to be our friend from these two traces for sure, because the feedback is a very sensitive analog signal. Just taking a look at the layout of the filter. So down here, that C1 and C4, those are those right angle capacitors. If you need to do it, we're showing kind of an implementation of how that would be done there. C2 and C3 are more in our what we'll call T-style type configuration on the input. D2 is just a TVS for low dump protection. D1 is our reverse blocking. Our ferrite bead, it's solid copper, so we don't have that in the test. And then we have our filter components C16, C17 in combination with L2 and C20. So keys here, we definitely want these components close to the input of the power supply. This will help with EMC. We've seen situations where if we move C2 and C3 away from the connector, it does have a negative influence on EMC performance. Again, this can be an option for orientation of these capacitors. I would highly recommend just checking with the OEMs on their configuration for this. We want to place these components, the filter components for the capacitors, close to the inductor and in a symmetrical layout. So we talked about the T-style in the session yesterday. We're trying to keep the impedance of these parts and the parasitics kind of the same so that these components look identical in the filter. And one thing we want to make sure is that when we're looking from the converter, the inductor needs to be the first component. So we want to prevent noise from the switching action, both the DIDT of the buck converter as well as the DVDT. So in terms of proximity, it's kind of electrically we're speaking. We do want to try and maximize the distance between the input filter and the buck if possible. That will help reduce some of that coupling effect we might have from the switch node into other areas of the circuit. Obviously not always practical, but we need to do the best we can there. So we've taken a look at different layouts in previous sessions, and you'll kind of see this change in color in this area, right? And this was kind of the board split, ground split type approach that we were looking at previously yesterday. And this is what we'll call a traditional layout. So we have 46.8 degrees temperature rise on this particular application. With the layout that we've taken a look at previously, this is now sitting at 40.7 degrees C temperature rise. So we've got about 6 degrees improvement in this type of PCB design. Obviously not huge, but this could make a big difference squeezing out every bit of power from the system. If you have to do a full 15 watts in the system, the 5 volts at 3 amps, 6 degrees could make a huge difference in some of these applications. So how do we stack up against competition? So you'll notice this is a very, very similar layout. So we're trying to take out as many variables as we can. The switching frequency is slightly different between these two cases. But you'll see on the left, the 4323 actually has better thermal performance than the competition. I mean, the circuit right down to the inductor value, all the layout, you can really clearly see that we're trying to keep this all the same. And we're about 4 degrees better than the competition in this particular case. So taking a look at EMC results, real quick, just pointing out the shape of the data that we see here. We can see the effect of the spread spectrum. So we don't see these clear peaks. We're seeing energy that's more spread out at our switching frequency. So our fundamental is somewhere around here, and the energy is spread pretty wide based on our spread spectrum technique. So in these regions, we've got about 10 dB of margin and 16 dB to the average. And this is basically on the left, we have a particular frequency range for CE. On the right, it's RE. On the top, this is 430 kilohertz. On the bottom, it's 2.2 megahertz. So that's how this is broken up. So at 2.2 megahertz, you can see we've got the fundamental spread out here and the effect there as it moves on to the higher frequencies. And we've got about 10 dB of margin at the higher frequencies on the average and 17 dB on the peak. So continuing on, this is RE. The horizontal is on the left side and the vertical is on the right. And then again, we have the 430 kilohertz on the top and the 2.2 megahertz on the bottom. And you can see as we move on, the higher frequencies are really not having an impact. And I don't have comparison to, say, another inductor with a tab coming up the side. But what I would venture to guess is if we redid this test with a different inductor where we have these metal clips that come up the side, we're going to start to see some issues at the higher frequencies. So certainly, if we were looking at the 2.2 megahertz. And going all the way up to 1 gigahertz, again, still lots of margin to the peak limits. So orange being the peak and green being the average. So this particular system is performing very well at the different frequencies. Again, 430 at the top and 2.2 megahertz down here at the bottom. So in conclusion, this particular design that we tested does allow a cost-effective single-side placement 2-layer PCB to perform well in the automotive environment. So we have basically full power out, looking at the 400 kilohertz range. We can do that at 100 degrees C. So this is a full 15 watts. And we can do 15 watts at 2 megahertz at 80 degrees C, right? And again, with the caveat, we need to have sufficient copper around the device. We did do the comparison of the 4323 with our competitors, and we are performing better. The device has better efficiency. So we are seeing a corresponding lower delta on the temperature rise. And we reviewed all of the EMC results up to 1 gigahertz, and we can pass CISPR 25 limits with this given design. So that's all I have. If there are any questions, I'm happy to take those at this time.
Great. Thanks, Mark. We did have a few questions come in during the presentation. The first one was, if you could move the inductor to be mounted on the opposite side of the board as the buck IC, could that help improve performance, i.e. by decreasing the loop area?
I would say in general, that's probably not going to improve the performance. It could potentially cause other issues because we would be routing the switch node down to the bottom. When we bring that switch node down, now we have that high DVDT exposed on the backside with a decent amount of area because we're going to have a footprint for the inductor. And in this particular case, I'm referring to this inductor for the switch node. So it is possible to still pass EMC in that configuration. I've seen that in different applications that are very space constrained. But it is a little more challenging, and you'll have to definitely take care on how the switch node gets routed, how much copper, how much ground there is around that switch node, and the orientation during testing as well could come into play.
Great. And then next one we have, let's see, clear that one. Are you using flexi-term caps for C7, for C6, 7, and 8?
To be honest, I don't know from the BOM if these are flexi-term. I believe they are, but I'm not 100% sure. That's generally an OEM requirement that you would need to take a look at, whether or not they require flexi-term or this 90-degree orientation, because it will affect your layout for sure. And these flexi terms tend to be a little bit more in price than a standard capacitor, but whether or not these particular components are in this design, I'm not 100% sure.
And then next one up here, regarding the input filter on this 2-layer board design, would it not be beneficial to put the filter on the bottom side of the board if possible in order to take advantage of the ground copper shielding to prevent unwanted unwanted coupling. I realize there may be DFM constraints that might prevent this.
Yeah, absolutely. I think in general, depending on the presentations that people have looked at previously over the last 2 days, you'll see in a lot of our EVBs that is actually the case. This is a very, I'll say, special case where we tried to keep everything mounted on one side to simulate a low cost application, where we're trying to squeeze every 1/10 of a penny, so to speak, out of our manufacturing, because it does add a little bit of more cost in manufacturing to populate components on both sides. But from an EMI perspective, you're absolutely correct. It would be better to place the input filter on the other side. Again, some of the other trade-offs we made was this particular inductor, it does have that bottom side mounting. You're not going to be able to optically inspect this connection, right? But that might be something that's necessary to pass EMC. And I unfortunately, I don't have the comparison data with a different inductor, but my guess is we will see some more emissions showing up in our EMI signature if we had a different inductor with a side metal clip.
All right, and then we have what factors contribute to the increased efficiency versus the competition?
I don't have a detailed comparison on hand, but I believe we have slightly lower RDS on in some of the MOSFETs. That's going to contribute to it, as well as we tend to perform a little bit better in this particular part with our switching losses. It's not, the switching losses are less of a factor. I believe it's the RDS on, but I don't have a detailed comparison.
And then we got a comment from your first answer that you just helped him win a bet. So good work there, Mark. And then the final one that I've got here was any observations on the effect of R2 on the EMC performance?
R2, let's see. So this is one of those trade-offs where it's going to show up both in the EMC, where we're going to see an improvement, but because we already have good results here on EMC, we don't really need that. The trade-off is going to be that resistance there in the bootstrap power supply is going to slow down the switching of the high side MOSFET, and that's going to translate into the thermal results. So we'll see as we decrease the EMI emissions, especially at the higher frequencies, we're going to see an increase in delta T here in these pictures. I don't have a good feel for, if it was 5 ohms, are we going to go up 2 degrees C? I'd probably have to do some testing on that, but for sure, the trade-off is going to be at the higher frequencies. You're going to perform better in EMC, but you're going to have degraded thermal performance in this particular case.
All right. That looks like the last one for this session. If you have any more questions, go ahead and fire away. We do have a little more time. We caught up a little bit, so I see we still have Todd in the presenter. I don't know, Todd, if you're available to answer any of the older questions. We'll still follow up with the email in case any of those people dropped off.
Yeah, hey, can you hear me?
Yep, I've still got you.
This is Todd. All right. Yeah, I can answer if you have questions, and if there's anything I can help answer now. If those attendees are still on the call, that's fine.
All right, well, let's take a crack at it, and then we'll follow up with the email as well. So okay. One of the ones was a fairly basic one. Does your chamber have absorbing tiles on the floor, or is it metal?
We have the absorbing tiles, from what I recall. Yeah, we have the absorbing tiles because we have some panels in the floor that we run the cabling through. So
Great.
We are, yeah.
Okay. And then this was one related to the quiz. In the quiz, the source is the electric field coupling from DUT. So how can we reduce or prevent it?
That's kind of an open-ended question. I mean, basically I was trying to show how we could reduce that or minimize it through, you know, some of the other things I was showing in the slides. But I mean, basically, the E field could be generated by different components on the board, such as the inductor or other, you know, switch node trace being too long or other electric field couplings. I mean, to reduce it, you may have to make changes to your layout. You may have to change components. In the worst case, if the E field coupling is too strong, you may have to resort to trying to shield that component or part of your circuit that is creating it. But I mean, there's a number of ways to mitigate it. It's just, you know, the main, I think the main thing I was trying to show is just, first of all, determining that your board was the main culprit in providing most of the energy that was being measured. And then after that, then you had to deal with it at a lower level by going through and trying to investigate each part of your circuit and determine where it's coming from. And then once you get to that point, then you can come up with one of several different measures to mitigate it.
Great. And another one from your session, Todd, was, did you ground the circuit board inside the shielded box?
No. I did no, for that test I did not.
And then another one was, if
the only ground connection in that was to the wire harness. So it was basically just putting a metal shield around the entire setup without trying to create any other kind of ground connections to it. So that was the approach I took. I mean, you could do it each way and try it that way too, but if you ground the board to the shield, then it could potentially change a lot of other things in your setup, and I was trying to avoid that.
Okay.
One
And
thing
this
to
one-
note there too, especially if the customer's trying to shield their application and that's done for actual production, many OEMs may not require a DC require a non-DC connection from that enclosure, that shield, to the PCB ground. So that's something to keep in mind as well. You may have to AC couple that ground.
Right. I mean, in the example I gave, it was with a board that was totally unshielded, and I was if it were an actual product that had a metal enclosure, a lot of times those boards will have some type of connection between the PCB ground, or, you know, a connector on the PCB to the enclosure, which you know, it can create some other behavior, I guess. You know, like on one hand, it can certainly help you at a lot of frequencies, but then some other frequencies it could hurt you depending on what circuit you're dealing with. And you know, you're basically, for low frequencies, creating like extra loops, extra circulation paths for the lower frequencies, whereas for the higher frequencies, it's acting more like a shield. But then if you have parasitics that are forming between the board and the enclosure, now you might drive more common mode noise out your cable, depending on how the board is fastened to the enclosure. There's a whole lot of, there's no easy answer for that. Like it needs to be like a case by case evaluation, but yeah, what Mark was saying is true. There's definitely different considerations. Different customers have different requirements. They may allow a DC connection between the metal housing and the board. They may not. They may have to use AC coupling. A lot of products don't have any type of metal enclosure. They may have just plastic housings, and then we don't have the luxury of using any type of shielding really. Then we have to come up with a different way to mitigate the noise. So those are all certainly things that need to be considered. But for the example I was showing, it was mainly to debug a board or a product that is not intended to have a metal enclosure or shielding around it.
Okay, and then I think the final one from your time frame, Todd, was if there's a first pass radiated emission results, but the chamber is not easily accessible for debugging, is there a quick way to debug the radiated emissions problem on the bench?
It kind of depends, like for the monopole.
Todd, are you still with us? I lost your audio. Mark, I know you're in the lab there with Todd.
Yeah, we actually went to different rooms, so we didn't have echo on the line, but I think he's in one of the other conference rooms.
All right, so let's skip that one for now. And then Mark.
I can add on to that real quick. I mean, I touched on that a little bit yesterday. If I go to my screen here real quick, there are some different tools and techniques that you can use, right? There are these field probes that would be able to connect to an oscilloscope. The caveat being your equipment and the probes need to be able to catch the frequencies of interest that you might be failing in those results that you have. But also keep in mind, there's going to be areas of emissions that may or may not be the root cause of your failing at that particular frequency. So it's something you'll have to take a look at. But there are tools that you can use on the bench, like these field probes, to take a look at different noise sources.
All right, and then Mark, switching back to a question that came in after your presentation. What happens if you eliminate the ground plane stitching?
In general, if we eliminate it completely, that's not going to be good for our EMC and our thermal. I think in this particular case, we could eliminate some of the stitching. I see 2 rows of vias around the inductor. We could potentially get away with 1, but in terms of minimizing our ground return currents and things like that, we definitely need some stitching near the capacitors, as well as good connection around the switch node to effectively minimize the amount of coupling we're going to have to other areas.
Yeah, sorry. Hey, Mark. Sorry, my audio cut out, so I lost both the audio and the speaker, and I just got it back. So I'm not sure where I cut out, but it sounds like you were helping answer the question. So yeah, let me know if there's anything else that's needed for that question.
Yeah, I think we got it covered by Mark, but
okay.
But if the person who asked that question wants to circle back and type in any clarifying, feel free to do so.
I did want to add one more thing to that. So when the tools and techniques that we've been presenting, we do have all of those available in the lab here in Livonia. So if you do have issues, you come in, you need to debug. We do have the field probes. We do have the current probes. We've got copper tape. And we do have the snap-on ferrites as well. So those are all tools that are available here in our lab.
Okay, and then back to the questions. Let's see, comment and question. All of the EMI mitigation techniques presented in these seminars are great, thank you. But I've also had a lot of success in using RC snubbers connected between the switching node and the ground. There is some efficiency trade-off due to energy dissipated in the snubber, but it's often acceptable relative to the benefit. Does MPS not recommend this technique, or was it just outside the scope of these planned presentations?
I can comment on what I presented, and basically, there's no reason why you can't try using a snubber to help in some of these situations. I think, just because we're limited on time with what we can present, we have to kind of narrow down the number of things that we're showing. And I think we try to show probably maybe some of the most common things that we apply when we're trying to debug. But yeah, snubbers can be effective. We're not against using snubbers. They can be effective, for reducing overshoot or ringing, which can contribute to EMI. And if you find that that's something that benefits you in a lot of your designs, then keep using that. It for high switching frequencies like 2 megahertz and higher, sometimes there can be the challenge of a little extra thermal dissipation. So for those higher frequencies, we probably try to avoid snubbers to some degree unless it's absolutely needed. But in some cases you may need it, and there's no getting around it. So that can certainly be an effective technique to use.
Okay, and then let's see, I've got Brent. Yeah, Brent, if you have any comment, feel free to unmute and go ahead and talk to this one as well.
Yeah, I'd like to add a little bit more on the snubber comment. Just from past experience, with any kind of EMC issue, you're always better if you can attack at the source, and rather than trying to absorb or mitigate. And what I've seen a lot of times in layouts, when you stretch that switching loop enough to insert an RC snubber, you've made the loop bigger, and it creates more ringing, more noise on the switch node that ends up getting radiated. So in a lot of cases, you can shrink that loop, get by without a snubber. A lot of people put footprints in from the beginning, so the loop gets bigger, so they do end up having to place that snubber. There's no good way to know without doing a layout, trying it first, but it's kind of a chicken and egg thing.
Great, thanks, Brent.
The other thing is we do with our packaging technology, the flip chip with the copper pillars, there's a lot of effort that goes into minimizing parasitic inductance and trying to make that switch node quiet as much as possible. But there is always that trade-off, and some parts switch faster, and depending on the layout, there could be that chance for ringing. So not necessarily a bad thing, but we do try and minimize the need for it.
Yeah, I agree. And the combination of the flip chip packaging, which we're using on a lot of our new parts, as well as the symmetric VN decoupling loops, the combination of those two things greatly reduces ringing on the switch node, as long as the switch node is laid out properly, per our data sheet or eval board recommendations. So that's why on a lot of our eval boards you don't see snubbers, because with a lot of our newer parts that are symmetric VN, we take great care in trying to make the switch node very short and making those decoupling loops very tight. And then a lot of these new parts are in flip chip technology, like Mark was stating. And the combination of all those things really helps reduce overshoot and ringing.
All right, and then I know we've been jumping around a little bit here, but Mark, going back to your presentation, this question was, in non-automotive applications, how does this device respond to conditions where the power connection is make first, break last, with the ground ASD make last break first?
Yeah, so it sounds like the ground connection would be done after the power connection. To be honest with you, that's not a condition that I've tested on a lot of our parts. That's something I think I'd have to take a look at. In general, I think there's protections on the device to help prevent bad things from happening, but I don't know if I can give a good answer right now on that.
Okay, and then going back to the ground plane stitching one, there was a follow-up on that. And that was, what happens when the surrounding poured planes outside of the main circuitry is not stitched?
Yeah, I would, in general, and I think we've taken a look at that on some of the other presentations, and we actually are working on some simulation material in terms of ground current density or current density in general, and the thermal design. But if you take a look at, it may be tough to see on your screen, but I think this is copy and paste on a lot of these vias up here. They're probably not doing a whole lot. I mean, when you take a look at the thermal images, that's the old layout, we start to get up in this region that is maybe, if this is 2 millimeter, we're approaching a centimeter away, and I think the thermal benefit you're getting from those vias is starting to degrade real fast. The current density around the part is also dropping off very quickly. I mean, it's pretty much going to be contained to this area. So the stitching, when you get a couple centimeters away, for sure is going to be not super necessary. But I would say I would still stitch in these areas, maybe not as extensively as what was done on these boards.
Okay, so I think that brings us to the end. So once again, thanks everyone for joining us. And we will be sending out the on-demand versions here in the next few days. And we hope to see you at any of our future